Hi, welcome to the Signal Path. In this episode, we're going to do something unusual. Some people on Patreon asked me to build a Nixie clock. Now, Nixie clock isn't something that I typically work on here on this channel, but I thought, hey, let's make one in a really crazy and unusual way. So first of all, I got a hold of this 5245L HP electronic counter. This is actually based on a Nixie tube display. There are 8 of these Nixie tubes in here, and it's a very beautiful instrument and it has a long and wonderful history. We'll talk a little bit about that throughout the video, but I want to turn this into a Nixie clock, and there's going to be a journey to try and get to that. So let's take it one step at a time and see what happens. Now, first thing, before I show you what's inside, I have to change the capacitors in here because they're really old, and turning it on could only potentially damage things, so I want to avoid that. So let's start with something basic. Just going to replace the capacitors, and then we'll go step by step exploring what's inside. So this is how I plan to replace these capacitors. Because there's no PCB, there has to be an elegant way to replace them and still kind of keep the original wiring and everything in place. So this is a 500 microfarad 75 volt capacitor. You can see they're very hard to take out without destroying them, but I made these little tiny PCBs, and then we can put a capacitor through here like so, and then this will basically replace this, and it has the same diameter, so it can sit in the chassis of the instrument like before. And if somebody really wants to keep the original look of it, you can cut these cans or buy these cans and then place them over this, and then it will look like that original one basically. So let's go ahead and replace all of these. So let's take a look at this instrument after I've done some of the modifications, and this is the bottom of the unit, and let's be amazed at the fact that this is hand assembled. I mean, I cannot believe that this was a realistic way to produce something so extraordinarily complicated and at such a high volume. I mean, look at these cable assemblies, all done by hand, and all the wiring. There is no PCB at the back of this. Everything is point-to-point wired. It's somewhere between the old style where everything was point-to-point and a hybrid between PCBs. You can see they're vertical here, and there's a whole bunch of stuff on the other side, which we will take a look at. If you look carefully, you can see that the modifications I put at the top, these are the capacitors in various places, and those plates allow me to just basically follow the kind of point-to-point wiring they had. Makes it fairly convenient. Some things are pretty cramped, so I had to work pretty hard to remove them and keep the original look of the instrument as much as possible. So there are some tests we have to do on the power supplies before we can really start testing to see if it works or not. But I'm going to zoom in a couple of places so you can see what happened to the capacitors. So there you go. So that's one situation there where we have 2 of the capacitors on the power supplies. Then these are a few more. These are the high voltage ones, 170, 130 volts, and then there is a circuit board here at the bottom and another capacitor there. This is the circuit board that controls the oven controlled crystal oscillator. I can give you a look at this wiring. Wow, that's absolutely incredible that this is all done by hand. And I put some deoxide and cleaned some of these contacts. It's probably going to need a bit more work, but I think it's in a good spot now for us to at least power it on and see if we get the correct power supplies. Now, there are some things which would never be allowed these days. These 3 pins are from the AC line, so that's live. One of these 2 is live, and these cables at the bottom, these thin ones, are basically touching this live wire. I had to separate them and put some zip tie to move things away from each other, but there is absolutely nothing covering these. The fuse is fully exposed, and if the live wire here comes in contact with one of these, let's say due to vibration over time, and pierces one of these and then makes contact, either the case will be live or it will destroy the entire instrument because there will be 120 volts everywhere. So yeah, of course a lot has changed since these things were manufactured like this. I also spent quite a long time cleaning the fan. I didn't want to replace the fan from this type to a more modern one, just to keep the original look. It is fairly loud, but it does have its own charm. So let's do some voltage testing. And here's the front of the instrument. You can see how much smaller the modern capacitors are compared to the old ones. These are all the ones I replaced. And I think they look quite good. If somebody really wants to put a cover on them, they can certainly do that, make them look original. Here's our oven control crystal oscillator. Here are all the boards that have all the counters on them. We'll probably talk about them a little bit later. Rectifier power supply board over here. The big transformer, of course, for the main. You can see the other side of the fan. And this is where the module sits, which we're going to take a look at as well. So I do have the schematic of this. It's available. So we should be able to look at the voltages coming from those power supplies, which power everything. There's about 5 or 6 different ones we can measure. All right, the instrument's powered on. No explosions. That's a good sign. So let's go ahead and measure all the power supplies. Let's start from the really large power supplies, high voltage ones. These are not regulated. So the first one is a minus 150 volts. That should be this one. And what do we have? Minus 152. Very good. So this is going to depend on my line voltage to some extent because they're not regulated. They're just rectified. And then we have another one that should be plus 180. That's should be this one. What do we have? Ooh, 194. So it's a little bit higher than it should be because it's rated plus or minus 10%. You might have to come back to that and take a closer look at it. Then the next one is minus 15 volts. That's an important one. What do we have here? Ooh, minus 24. That's definitely a problem. So we're going to have to take a look at that. That's supposed to be regulated, so it should be much more accurate. Then we have a plus 13. I think that's this one. Yep, plus 13. That one looks good. Then we have a plus 20. That's an important one too. I think a lot of logic runs off of that one. I think that's this one. Plus 20. Very nice. That one's spot on. Then we have minus 6.9, which is on a different module. Here it is. That's accurate. That should be plus or minus 1 volt, so it's really close to where it should be. And then we have plus 17.6. which is another important one. It should be somewhere around here. So 15, 14, 13, 12. Yep, so the plus 17.6 is also not good. It's sitting at 6.7. Now here in the manual it says that the last two voltages depend on the plus 20 and minus 15 volt power supply. But our minus 15 volt power supply isn't working. We're getting minus 24. So that could explain why the other power supply is wrong. So let me turn this off here and take a look at the schematic if we can guess what the problem could be. So here's a portion of the schematic that we need to worry about. There are three unique power supplies that are regulated here. There's the 13 volt supply, the 20 volt supply, both of those were okay, and the minus 15 volt regulator here. That's the one that's a problem. Now all of them are coming from various rectifiers. Nothing really unusual about these, and the capacitors that I replaced, the large ones, are these ones. These are the electrolytic ones that are essentially were all failing. I replaced them. So we have to pay attention to this. Now, if you look at what happens to this regulator, is that it has this transistor Q2, which is the main regulating transistor, and the 15 volt is generated right after that. It starts from roughly 26 volts going in AC. That's rectified out, stored on this capacitor, and then this entire dotted area is a separate board that does the different regulations. But this is a very common voltage regulator situation. And of course, back then when these things were being made, voltage regulators weren't available in integrated fashions like you see here. Everything was discrete. So they had to basically make a voltage regulator from discrete components. So the 15 volt is sampled and divided here. You can see that resistor R5 can be used here to actually adjust that voltage so they can fine tune the minus 15. I tried playing around with this, it does nothing. Something else is wrong. Then we have a zener over here and a zener over here. These are going to act out like our references. But the feedback path goes through this transistor, through this transistor, and then adjusts this guy. So that's kind of our closed loop system of our regulator here. Now, if this is about 26 volts here, which means we are looking at the voltage here, which is now minus 24, being very close to this side. I have a suspicion that this transistor Q2 is dead. Now, if this transistor is not dead, by the way, if this is failed, it means this collector and emitter would have to be shorted together in some way, or with very small resistance. Or it could be that these regulators here are just maxing out this voltage, and then that causes this to fully saturate and just pass through as much as possible. Although the fact that the voltages are close to each other, it's a little bit more unlikely here. So I think we can simply go ahead and make a few measurements on these devices. It's not a very complicated circuit. I'm sure we can find out which of these components need to be replaced or perhaps some other issues there. Let's go back and try it. So if we are sure about this, we should be able to measure a short circuit on one of these transistors. Now these are the three transistors that are responsible for the various power supplies, and the top one is the one that we've been looking at for the schematic. So I'm going to try and see if I can find a short there. The short should be between these two terminals. Let's give it a try. What do we have here? Look at that. I think it's a short. There it is, 0.5 ohm. That's indeed the short circuit. It's exactly as what is expected. Now we can look at the other ones to make sure they don't have a short circuit, and they should have a totally different resistance. 85 ohms, that makes sense. And for this last one, let's give it a try. Gonna have to make some good contact here. Some of these pins are fairly corroded. And there it is, 260 ohms. So definitely, we're going to verify one more time just to make sure that it is indeed a short circuit. And if that is, we have to replace this device. And here's the suspect device. We're going to go from the collector to the emitter. And what do we have? Yep, indeed we have a short circuit. Okay, so that transistor is dead. So I didn't have the patience to wait for another one of these modules in these kind of package to come back. So I just decided to take a regular PNP device and use the chassis, the body of the old transistor, and just replace it. And this is now soldered to this body, so the thermal solution from the body of this transistor to the chassis of the original one should be very good. So we should be able to put this back in. Now this is pin compatible in exactly the same way. I also checked to make sure that the current handling of this device and its parameters are compatible with the old one. That was a really old transistor, so it's not difficult to get one that has even better, much better performance, of course. Let's go ahead and put this in and see if the power supplies recover. All right, the installation is complete. Now we can measure the power supply. So we're expecting minus 15. And what do we have? Look at that. Perfect. So it is working. Now we have recovered the power supply. We should do some further testing. So according to the sticker on this thing was calibrated last about 40 years ago. And here's the oven-controlled crystal oscillator that's in this unit. It's very large. I believe the L version of this unit uses a 1 megahertz crystal, and the M version, which is essentially the same instrument with just a better time base, uses a 5 megahertz crystal. Now both of them have a coarse and a fine variable capacitor, which allows you to tune it and pull and push the crystal a little bit away from its natural center frequency. So we should be able to measure that against a rubidium standard and align it so that it is exactly at 10 megahertz, so that we can measure something very accurately from an external source. Let's try that. Alright, let the unit run for a while. I also closed it up so that its thermal situation can stabilize, and turn it the right side up so that the effect of gravity can be removed from the crystal. And not too bad, it's off by about 3.4 hertz over this 40-year span, which is really not that unusual. So let's go ahead and try and adjust it, see if we can get it as close to 10 megahertz. And there we are. I think that's good enough for our experiments. So we can test our HP5245L using the Tektronix TSG 4106A. I've done a full teardown and review of this instrument. You should definitely check it out. It has a very good time base and oven-controlled crystal oscillator. The architecture of the instrument is based on Stanford Research Instruments itself, and it has a very good time base. So right now we're using the low frequency output at 100 hertz. It's not enabled. We are on the 1 second time base here on our instrument, and the sample rate, you can see it every once in a while it does the sampling. Right now there is nothing, of course. Let's turn it on and see what happens. There we go. It's counting 0.1 kilohertz, which is 100 hertz. There's something so satisfying about Nixie tubes counting up to something. And the reason it's counting is because I didn't enable the storage mode, and it's showing you as it counts forward, which I think has even more charm to it. So it works at 0.1 kilohertz. Let's increase that frequency now to 1 kilohertz. Here's 1 kilohertz. It's going to count a little bit more. No problem. Let's do 10 kilohertz. And it was in between. 10 kilohertz, no problem at all. And 100 kilohertz. There it is. Very nice. 1 megahertz. So cool to see it count like this. And 10 megahertz. Oops, that's 10 kilohertz. Wrong one. There's 10 megahertz. Let's see. Look at that. It's just missing a little bit. Occasionally a couple of digits. There we go. And 50 megahertz, I believe, is close to the maximum this thing can do. Let's see, 50 megahertz. There you go. Yep, missing a couple of digits there, and a couple of hertz at the back. Very nice. Now the time base inside of the 5245L, it drifts around. And normally, if you want to use this in your lab nowadays, you would just connect maybe a GPS discipline oscillator or even a rubidium reference to it instead of using its own internal one, which you can get much better than what's inside of this. And we're going to try that just to see it give a more accurate result here. We can go ahead and change the time base here. There you go. You can just move the digits down. 50, still 50, and it should be 50 one more time, and 51 last time. There you go. 15 megahertz. I don't think we can go much higher than this. Here's 60. Well, it works at 60, 70. Nope, it doesn't. It could be that we need to increase the amplitude a little bit because probably there's too much attenuation in the front. We can try that as well. I'm going to make it 1.5 volt RMS. See if it counts. Oh, actually it can't go over 1.1. No, it can't. That's the maximum. Okay, I think it might be just too much attenuation for it to trigger and catch it. But it looks very nice. Let's go back to 60 there. There you go. Very good. Let's go back over here. There is our 60. Now, just to make sure everything is working, I'm going to use the 10 megahertz reference output of this, connected back to the input of this one, use that, and now they're locked together, so it should never give me anything other than the exact number that's written up there. Let's try it. Well, I ran into a tiny problem. The internal reference of this is running at 1 megahertz, so it requires a 1 megahertz reference signal, not a 10 megahertz one. And these instruments, of course, produce a 10 megahertz reference. So instead of what I did is I'm using an Agilent 33250A here. I locked this one with 10 megahertz to this one, I'm generating 1 meg from this, feeding that into the reference of this, so they're all actually locked together. This allows this 1 megahertz signal to be derived precisely from the 10 meg reference of this one, and therefore this one has its reference now locked to this one. Hopefully that makes sense. So now if we enable this, we should never see anything other than precisely 50 megahertz, which is exactly what we see. All the error is gone. This means that with a good time base on this that is accurate, you will not have any offset with respect to whatever time base you're inserting into it, which is great, which means everything else is working. I also have the full service manual of this instrument, and there are a lot of fascinating things we can go into and talk about how the engineers thought about designing this instrument. Keep in mind that when this unit was made, the transistor wasn't available for very long neither. It was basically a brand new invention itself, and for them to use so many transistors in this and to create something so complicated was a massive engineering undertaking, and very bold, and which is of course what HP was known for. Now the concept of this frequency counter is really straightforward. You essentially have some gate control which starts and stops a counter. So you're just counting every time there is a cycle on the input signal, and you count for a certain period of time and then you stop. And then you can calculate the frequency based on that if you have a certain time base that you know the frequency of, which is what the oven controlled crystal oscillator is. So really that's all there is in there. Now the block diagrams and the functional diagrams are really complicated. There's a couple of interesting things I think we can look at. For example, the way they used to make gates, because remember, transistors aren't as common, so they were making OR gates and AND gates and inhibit gates and kind of limiters and regulators, all using just simple diodes. And this was common because that's the only way to do it. Nowadays these things are so everywhere, and then we take them for granted. They were quite difficult to make back then. Another interesting thing to think about is, here's various kinds of flip-flops using only 2 transistors. Not sure how well you could call this a flip-flop. You have to assume a certain pulse coming in, and you have to have diodes in it for it to make it work, and trigger circuits and so on. But probably my favorite thing in this whole service manual is this portion. They're using neon tubes and photodetectors like a memory cell. Now, neon tubes have this property that once you turn them on, because again they're not solid state, so once you turn them on and you ionize the gas, you ionize the neon gas, then the voltage across the device changes. So in a way it has negative resistance. So you could store a bit of information in the fact that the voltage across the device has changed once you fire it, once you strike it. So they're using that in order to store a bit of information. So they light up the diode and they look at a photodetector on the other side, and depending on the signal on the photodetector, they can tell what value was stored in it, which is a fascinating thing. I really recommend that you go and look at that. There are multiple of these circuits inside each of the Nixie tube drivers, and that's how they store the values so that you can look at a single frequency count without looking at it counting up. I'll see if I can demonstrate this briefly, if I can find a good neon tube to show you, but essentially they're using the negative resistance properties of this. So here's an example to see the difference between the striking voltage and the maintained voltage, the negative resistant aspects of ionizing gas-based light sources. I have one over here. This has an internal coating that makes it glow green, but it's essentially based on the same principle, even though the color is not red like we're used to with the neon light source. So I'm going to go ahead and run a sweep. The sweep is going to run from 25 volts to 125 volts. I'm going to monitor the IV characteristics of it. Let's go and try that out. Here we go. So at the very beginning, there's going to be essentially no current. You can see this current on the left side is in the picoamps right now, and the voltage is increasing. 48 volts, 51 volts, and the current is going to steadily increase. And at some point, you'll see this light up. And as soon as it strikes, you'll see the voltage drop significantly. We're actually limiting the current to 1 milliamp. There you go. You can see it's lit up. So we have up to about 84 volts, we get nothing. But as soon as the gas is ionized and we have glow, then the voltage drops down by about 20 volts or so. And that difference is what is used in these kind of instruments to measure and to store a bit value that's actually stored in that memory cell. It's a very clever technique, and that's the best they had at that time, of course. Now, a useful modification to this instrument would be to allow it to operate with a 10 MHz external reference. Now, one way to do this would be to change the 1 MHz OCXO built into it and modify the circuitry, allowing for it to operate from a 10 MHz reference. But I really don't want to do that. I want to keep the original circuit here. It's okay if it's running from 1 MHz. What I really care about is being able to put a 10 MHz external reference really to lock it to other instrument. So maybe adding something to it that can divide, for example, an external circuit coming in at 10 MHz down to 1 MHz, and then the rest of it essentially remains unchanged, operates exactly as it is. Well, I looked around some of my old equipment and parts, and I found exactly the same connector, an additional one, a spare one, that from some other old instrument, and I added it to this. So my goal is to add now one of my own cards, a card that just plugs into here, that does this 10 megahertz to 1 megahertz conversion, essentially divide by 10 circuit. And then we can replace the external connector going into this board instead, and then from this board back to where it was. So I already wired it on the other side. So let me show you how I did that, and then I'll show you what I made in order to perform that function. So here is that additional connector that I added. This is new now, and you can see I have rewired some of the old ones that were going through this area back onto this. So this allows us to steal one of the power supplies from the backplane as it is and use that to power our own circuit. So really it fits very nicely in the original architecture of this thing. You can't even tell that it was kind of aftermarket. And there's two connectors here, two coaxial cables going into it. One of them is routes all the way down here, and I'll show you where it goes, and the other one just comes back all the way this way. So basically 10 megahertz goes in, 1 megahertz comes out, and everything else is just power supplies. And that allows us to make that division. If we go over here in the corner, this is where you can insert the external 1 megahertz reference. So now this instead goes all the way up to that card, and then the signal coming back over here goes to where it used to be connected. So nothing else really has changed. All this does is it allows me to put in 10 megahertz, which is quite convenient. So let's take a look at that circuit now. And here's a little board that I made to perform the divide by 10 function. And I CNC'd this little motherboard at the bottom, which then plugs into the connector that's in the instrument. And you may ask, why didn't I just put all of these components on top of this? And that's because when I originally started working on this, I didn't have that connector, so I wasn't planning to use anything like that. And by the time I was done, that's only when I found it, and then I just simply decided to create this layout for this board and then connect all the cables from that to this to perform all the functions that you saw. Now 10 megahertz is a very low frequency, so dividing 10 megahertz by a factor of 10 to create 1 meg doesn't need any fancy RF circuits. You can just use some basic digital counters. So if you have a counter that counts up to 10 and then resets itself, every time it resets itself, it represents a divide by 10 function. So that's exactly what I've done. I have a counter over here. This chip is actually an 8-bit counter that counts from 0 to 255. Now, if I don't do anything, every time it counts to 255, it will reset. And when it resets, it creates a little pulse, and that pulse tells you that the counter has rolled over. But you can also input and set the starting point of this kind of counter. So instead, I'm just simply setting it to 255 minus 5. So it will count from 252 to 255, and then it would reset. Now that's only a division by 5, it's not a division by 10. And the reason is because the output of this is a pulse, and that pulse is narrow. It's only one period of a 10 megahertz signal. What I really want to generate is a nice square wave at 1 megahertz. So then I take that pulse and I put it into a flip-flop who is in feedback, and that creates kind of like a JK flip-flop, and that creates a divide by 2 function, and divide by 5 times divide by 2, that's divide by 10, and we get a nice square wave output. If you're interested in the schematic of this, I can make it and put it on the website. Just let me know in the comment section. There's another chip over here. This is just a basic Schmitt trigger inverter, and it allows me to create any signal that's coming in, turning it into a nice square wave, and it also buffers the output of the flip-flop so that it's once again protected. Now, another thing you need to keep in mind is that all of these circuits are running from a positive power supply voltage. I want things to be zero referenced that go above and below 0. So everything is AC coupled. That solves that problem. So we have a 50 ohm termination over here. We have an AC decoupling capacitor, and I have a potentiometer in here which sets the DC voltage at the input of the Schmitt trigger at 2.5 volts, which is exactly in the middle. That means that any voltage above and below it will eventually create a square wave out of the Schmitt trigger inverter, and the output of that is also AC coupled through this little capacitor over here, so it goes back into the circuit. So everything is separated DC from the outside world. There's also a 5 volt voltage regulator, a couple of decoupling capacitors, and LEDs so that we know it's turned on. And again, if you like to see the circuit of this, I can draw it up and put it on the website. It's a nice, simple little divide by 10. So let's go ahead and plug this into the circuit and test it to make sure it's actually working. And something neat to consider is that this thing, even though it uses very old ICs and our through hole and everything, is now the most sophisticated piece of semiconductor engineering in this instrument by a wide margin. It's a neat little thing to consider. And here it is, sitting inside the unit. So let's do a quick test to see if this division circuit is working or not once it's inside the instrument. So I'm using the Keysight DSOX3104T as both the generator and of course the oscilloscope to measure those signals. I'm using the arbitrary waveform generator built into it to make a 10 megahertz sinusoid signal. I'm feeding that back into the reference input of the instrument, now at 10 megahertz, and I'm monitoring it on the other side using channel 1 of the oscilloscope. On channel 2 of the oscilloscope, I'm looking at the return signal, the signal that now should be at 1 megahertz, the divided down. You can see they're very close proximity of each other because originally this reference input was directly connected over here. So right now I have enabled the waveform generator using this oscilloscope here, and you can see we have a 10 megahertz signal. It's not very sinusoidal. That's because the power supply to the CMOS chips are actually turned off, and some of the built-in ESD diodes at the I/O pins of these chips are actually reverse biased, and that's why the nonlinearity is there. It's not really a problem because we do have some series resistance and everything in there. Okay, so let's go ahead and turn on the instrument and see what happens. There we go. So we get now some activity on the second channel. I'm going to have to change the trigger to trigger on the second channel now. And if I do that, check it out. I think it looks pretty good. Let me turn this off so you can see better. There is now our 1 megahertz signal. You can see that it does say 1 megahertz over here, and on channel 1 we do have our 10 megahertz input. So indeed it is doing exactly what we want. It's generating a 1 megahertz from a 10 megahertz input. And let's do one other quick measurement to make sure that this divider is dividing accurately, because it's difficult to see that on the oscilloscope. Of course, we need to measure its frequency. So here I'm using the RFG-RB. This is a rubidium 10 megahertz standard. It's generating a 10 megahertz signal from here, which I'm feeding back into the instrument itself, and I'm monitoring that signal. And you can see over here on the frequency counter that we're indeed very, very close to 10 megahertz. These are two rubidium standards being measured against each other. They haven't been calibrated for a long time, but it's close enough for our purposes. Now I'm going to switch that from a 10 megahertz input to our divided out 1 megahertz output. Let's see what the actual frequency counter is going to say now. It's going to take 5 seconds to stabilize because I'm measuring over a very long time. And look at that. It's exactly divided by 10. So the frequency is very nice and stable. It's precisely divided by 10, and it's not moving around. And I did this measurement for some time, and it is within the stability of the actual source itself. So I'm quite happy with that, and we should be able to now do our clock. And Dr. Pooch is, as always, supervising, making sure that the measurements are done correctly. Good Pooch, you're sitting at the tallest point in the lab now. So hopefully by now it's become clear that I intend to build this Nixie tube on the frequency counter by using some external synthesizers. Essentially, I'm going to set the frequency of these external synthesizers such that numerically they represent the current time. And we can change it every second so that it keeps updating, and then therefore it's going to look like a clock. I'm going to use this ERA Instrument EasySynth++ here on the left one. This is a 20 gigahertz version of this, which is a huge overkill of what we were looking for, but I have other very interesting plans for these synthesizers in the future. I actually have reviewed the EasySynth Micro on the website before. It's a very handy little synthesizer up to 6.4 gigahertz with an LCD screen, runs from a battery. I've been using it around the lab all the time because it's just so convenient. This is its bigger brother, much more capable in terms of its performance, and it goes of course to 20 gigahertz. It has built-in Wi-Fi and a whole bunch of other features. So let's take a look and see what's actually inside of this, because it's a fairly good design and it uses some really good components off the shelf. And I want to talk about the architecture of this since we're going to use it. And once we take a look inside this, then we can hook it up to our Nixie tube clock. All of ERA Instrument products are open source, which means the schematic, block diagrams, the firmware, and all the interfaces to modify the firmware and reprogram the unit are completely available to the end user, and no registration is even required. It is based on an Arduino compatible chipset and an ESP module which has Wi-Fi built in it, which means you can have your own web interface built in, which it actually has one, and you can control the unit using that as well. Now the reason I like this unit for this purpose is because it does have a serial interface, so you can send a serial commands and adjust the frequency as you see fit, which adds again additional flexibility, and you can even write your own commands if you wanted to. The architecture of the instrument is fairly classic, but it does use some very high performance components to achieve very good phase noise and so on. So let's take a look and see how it actually works. So we do have the reference in coming in at 10 megahertz and a reference out at 10 megahertz, and we're going to use this reference out to synchronize this synthesizer with our frequency counter. That way the exact frequency will be displayed as I showed you earlier, and that was the reason why I needed a 10 megahertz reference on the frequency counter. Now you can switch between that or the built-in TCXO or CXO. In this case, we're going to be using the internal one, of course, and you can switch between the temperature compensated version as well as the oven controlled one. Now once you switch that in, you're going to switch it into a PLL. This is our first PLL based on a VCXO running at 100 megahertz. This allows you to lock this VCXO to the external 10 megahertz reference and achieving a certain frequency accuracy and stability. The loop filter characteristics here are adjusted such that appropriate frequency locking is achieved and some phase noise characteristic behavior is passed forward. This is a multi-stage PLL and very typical that you have to adjust different loop filter bandwidths to accomplish whatever phase noise that you're looking for, a certain profile that you're looking for. And that's 100 megahertz and is divided by 10 in order to produce a 10 megahertz. So you get this 10 megahertz directly based on this 100 megahertz signal. Now this 100 megahertz signal then becomes the reference to the next stage. Now they're feeding that into this chip over here, which is a DDS. It's a direct digital synthesis stack, allows you to synthesize any kind of frequency you want. And these frequencies can be very low as 100 hertz all the way to 103 megahertz. This is also a common technique to generate a very flexible reference frequency, which then can be fed yet to another PLL, and therefore by adjusting that you can get any frequency with a very, very fine resolution at your final RF output. Now both of these components, both for the reference generation and the PLL with the built-in VCO, are critical to the overall performance, and I'll show you what's inside one of these. Now this component over here can generate signals from 6 to 15 gigahertz from one of its ports, or as high as 10 megahertz to 6 gigahertz from one of its other ports, and these are all controllable through some SPI interface that this chipset has. You can see this one has its own loop filter as well, just like this one has its own loop filter. So there's multiple characteristics here being added to each other. Then after that you have switches to select between the very, very low frequencies, because they need some divider to reach very low frequencies as low as 250 kilohertz, and then multiple switches, amplifiers and attenuators, and then ultimately the RF output. Now what this instrument doesn't have is a bank of switchable filters in order to achieve extremely high spurious-free dynamic range. So you will see harmonics and tones, and some of that may not be appropriate for your application, but for the cost performance, this is going to provide some excellent value for the money, and that's essentially its intended market. And for many applications you could add a filter if you're looking for something really pure, of course, but in general this shouldn't be an issue too much. Now if you look at over here, the full schematic is here for the instrument. I'm not going to go through the details of it right now. We're going to talk about this unit later in some other plans I have for it, but I do want to show you what's inside of that core VCO PLL chipset. This is from TI. It's a fairly expensive part, and it is using a fundamental VCO up to 15 gigahertz. That itself will give it very good performance around those frequencies, and then you can divide that down for all the lower frequencies. So because it's not using a doubler, and because of course it doesn't have its own filter, not having a doubler there has a huge advantage in its harmonic performance already, which is quite good to see. This is one of the best I think you can get currently on the market, with a 45 femtosecond RMS jitter at 7.5 gigahertz, which is integrated over a really wide bandwidth from 100 hertz to 100 megahertz. Excellent performance synthesizer. So we're going to use this for a lot of other applications, but at least now we know what it looks like architecturally. We should still take it apart and see if we can identify these components. So let's take a look and see what we have here. They've done a really nice job, by the way, on the chassis of this unit. Very nice machined aluminum piece here. And here's the board, and it looks very professionally done. And if you look over here, this is our Wi-Fi module. It is a bit unusual to have a source of RF generation inside of a synthesizer, but you want to keep everything very clean. And it looks like they have placed 4 screws all around it in order to really hug this little chamber here so that nothing leaks out. This is something we are going to have to test further once we have a more review of this thing. And then the output is on the opposite side, so there's some isolation there. Now if you look at the number of components, we can immediately recognize the architecture from the block diagram we were looking at. We have 2 USB ports over here. This portion is the DC-DC converter portion dedicated for power, and here we have our Arduino compatible chipset, which then can also be used to program this ESP module as well with Wi-Fi. It's essentially all digital at this point. Now here's our references in and out, and you can see our VCO here, our OCXO here, and then the output of these two generates our 100 megahertz reference. That then goes on to, here is our main variable reference generator using DDS. Here's our main PLL, low phase noise, phase frequency detector over here, and all the switching networks in order to get the output eventually over here, some amplifiers and some switches and attenuators in this region. So it really nicely matches what was on the block diagram. So now that we have a good idea what it looks like on the inside, we should go back and use it on our clock. And here is then the setup for our Nixie tube. So we have the ERA Instruments synthesizer here at the top, controlled with the USB here. I have the RF output directly connected to the input of our frequency counter, and the reference 10 MHz clock goes out back into the instrument, which now of course it accepts 10 MHz. So let's take a look and see how the code creates a clock out of this frequency counter. And here is our clock in 24-hour format, so it is 4:37 p.m. and the last two digits are the seconds. Now there are some subtleties here that you have to keep in mind. We don't have any synchronization between when the frequency switches on the synthesizer and the gate on the electronic counter. Now this gate does have an external one, so you can externally gate this so that you can synchronize this with some other instrument, so that you don't make a measurement while the synthesizer is switching. That's why every once in a while you will see the last digit jump around a little bit. You can play around with the time base as well as the sample rate to get somewhat of a accurate result, but it works really well. There you go. There was just that one situation you saw jumping back and forth. That can be fixed with an external trigger, of course, but it gets the point across. As far as I know, this might be the most complicated way anyone's ever built a Nixie tube clock. I'm not sure if you know otherwise. Please let me know in the comment section. But there is a lot of other things you can do. As long as you can create a numerical representation using a synthesizer, you can do a YouTube counter or the date, or you can switch various types of data. It's too bad that this doesn't have any alphanumeric values, otherwise you could show messages or whatever else you wanted as well. I think it's a cool little project. Really, the purpose wasn't to make a Nixie cube. It was mostly so that we can go through the design and architecture of a frequency counter like this one and contrast it with the new technology and play around with some of this beautiful HP hardware that was designed, many years ago. There are other things that I want to talk about perhaps in future videos, like these frequency converters, which operate on a really fascinating principle with a tunable cavity. This is what they had to do back then in order to create something that can down convert a frequency within the range measurements of the counter itself. I've talked about some of that in some of the other frequency counter, more modern versions of this instrument that I've looked at, but this is worthwhile taking apart and talking about too, and I have a couple of other modules we can explore in the future. And there you have it. I hope you enjoyed this video. It was fun to work on this instrument. Of course, if you have any other ideas, let me know. And as always, thanks to the Patreon supporters. You're the reason why I'm able to get all these things together and actually build these things to explore the circuits, the architectures, and how these instruments are actually put together. As always, I'll talk to you in the comment section.